Hello, and thank you for taking the time to listen to my talk today. So my name is Matthew Howard, and I'm from King's College London, where I head up the Robot Learning Lab at King's. And what I want to talk to you about today is empowering growers to exploit adaptive robots. So I'm going to tell you some of the efforts that my group has been making in trying to bring automation to the horticulture sector. So some of this work is sponsored by various bodies such as the EPSRC, the HDB and Vitagress Herbs. So I want to start by highlighting what is the current practice in horticultural production, and this is pretty UK centric because these are the kind of businesses and the companies that we work with. So this video, or these clips of videos that you're going to see here, are taken from a medium-sized protected ornamental horticultural business in the southwest of the UK. And the kinds of tasks that you can see here are things like grading, collation, and so on and so forth. So essentially they're processing these ornamental plants and making them ready for retailers. So they're doing things like taking out unhealthy specimens, doing some inspection, replacing the unhealthy ones with healthy ones so that you get a complete high quality plant tray, taking clippings. These clippings might be used for growing on and producing more stock. And I think, as you'll see here, that it's quite a lot of dexterous manual labor here. And the kinds of things you're having to deal with here are, well, firstly, a huge variety of plant types. So different species of plant, from this grassy type thing that you can see on the screen here, to more leafy plants, succulents, and so on and so forth. So you've got a really challenging automation problem to be able to deal with these, the huge variety of different plant material. So what can we do to deal with this? Where are there solutions? So obviously we're interested in robotic solutions, and the particular area that our group has been focusing on over the last few years is that of collaborative robots. Robots that we're able to teach, so robots that can learn from some kind of demonstration. So here we can see one of my former students who's teaching this robot how to pick out unhealthy plants and dispose of them in a plant bin on a grower site in the UK. And this is actually, this is a task that you saw from the clips earlier, and this is a task that we actually use as a test case, and I'll talk more about it a bit later on in the session. So learning from demonstration, well, I think people are very familiar with how learning from demonstration works in the robotic domain. So essentially you start with demonstrations from people, you gather data of some sort, and you, from that data, build up models of controllers, sort of objective functions and so on. Those models get fed back so that we can derive a controller for our robot and for our task. And once the robot can try and perform that, and if it does well, then great, and otherwise it will need to it can potentially close a loop and come back to the human for further demonstrations. And of course there's lots of different flavors and types of this kind of learning from demonstration, but the thing that I'm particularly interested in is the human part of this loop. Okay, so I think we've done a lot of research in the kind of algorithmic side of how to develop good learning algorithms that are effective, but we've spent relatively little attention to this very key component of the loop. So I'm mainly interested in how can we make it easy to give good demonstrations. Considering our target users here are general nursery workers, they may not have had a technical education, they may have never encountered a robot in their lives. How can we expect them to sort of be given a robot and work with it effectively? Now I think that we have some way to go to kind of improve that interface. So in a bit more detail, or a bit more sort of precisely, we've got a teacher and a learner interacting with one another. So the teacher is generating data sets, we're going to call them little b, from the teacher's belief about the behavior, about the robot's current state of knowledge, maybe some internal bias factors, and any data that the teacher has already provided as demonstrations. Those demonstrations are passed to the learner, who then derives some kind of controller or control policy, from the demonstrations. And then using that policy, we can get feedback about what the robot's learned by basically executing that policy and producing reproductions, and we're going to call them kind of little r here. Okay, and those little r, these reproductions, they're going to be sent back to the teacher, so the teacher can observe what the robot is doing. And then the robot is the teacher, is essentially interpreting those reproductions. Okay, so it's forming a belief of what the robot state of knowledge is, maybe including some internal biases, but based on the reproduction data that's coming back from the robot. So this is the interaction that we're talking about here. And so if we want to make the teacher do well in teaching the robot, then arguably the thing that we have to control is this bottom right hand corner here. Okay, so essentially we're asking that question: how should the robot feed back to its human teacher? Okay, so how can we choose good policy execution? So the policy is determined from the data, the policy is learnt, but we still have some flexibility in choosing how we demonstrate our policy. How do we show what we've learnt back to our teacher, so that hopefully when they interpret our behavior, they come up with better data set to improve our learning of the policy. So within the context of grasping and manipulation in horticulture, we've been conducting some studies to try to understand how this can work, how this can sort of improve practical teaching skills for the kinds of horticultural tasks that that growers care about, essentially, right? Because in the end it's going to be growers using these robots, and it needs to be growers that are able to teach them tasks. So we've got to think a little bit here about what kinds of issues are they going to find. So let's focus in on this plant disposal task, so removing unhealthy plants from the tray. The first thing is that we want to probably enable some kind of generalization. That is to say, we don't want to have to teach the robot every single picking behavior that it needs for all of these 100 tray positions. Rather, we'd rather give it a few key demonstrations, let's say these cyan lines, and from those it should be able to generate the right kind of picking behavior for other plants in the tray. Okay, so that's it's a simple problem to address. You might think, well, generalization is kind of obvious to us in the robot learning community, but I guess the question is, do non-technical growers understand this problem? Would they be able to teach this robot effectively? So to evaluate how novice general nursery workers working in the sector might actually interact with that behavior, we set up an experiment where we had that plant disposal task, and we compared different types of feedback mechanisms from the robot to the teacher. Okay, so the details are here on the slide, but the four kind of main cases that we were interested in are the no feedback case. So a participant just gives a batch of demonstrations and doesn't get any feedback during the teaching, and then we just have to evaluate how well the robot does. So how good was that teaching? So this is kind of our control case. And then we compared three kind of in-teaching feedback cases. One of them we call replay feedback. So that's where a participant taught a picking behavior from one of the plant locations, and then immediately after giving that demonstration, the robot replayed its policy to pick that same plant. Okay, so that's immediate replay of the last demonstration. We looked at a batch feedback approach where we chose some points that we thought would be good for indicating generalization. So these are indicated by the red circles on the picture here. So we essentially looked for the 4 corners and a middle point, as that kind of gives you a bit of coverage over the plant tray. So after every demonstration, the robot showed what kind of picking behavior it would do for these 5 batch points. And then we also allowed selected feedback. So this is the 4th case. In this case, teachers were allowed to choose a point from which the robot should show its behavior. Okay, so for example, you could teach the robot picking this plant, and then the demonstrator, the teacher, could say, well, show me what you would do for this plant. Okay, so they've got that flexibility. Participants were free to choose the location and the number of demonstrations that they made. And the teaching efficacy was measured using a metric on the wrist distance between, distance between the wrist and the pickup and the drop-off point. Okay, so in these plots up here, you can see the red line. That's a distance between the position on the plant tray that we were aiming for, and the coloured dots are the actual positions of the pickers. And then efficiency is simply measured as the efficacy over the number of demonstrations given. So the interesting thing was that actually the only case where we saw a significant increase in the teaching efficiency was when we gave batch feedback. Okay, so in all other cases, we had roughly the same level of efficiency, so no feedback and replay and self-selected feedback all sort of achieved sort of between 10 and 15% teaching efficiency overall, whereas the batch feedback was kind of up in the 25% teaching efficiency levels. So this is kind of interesting because it means it sort of shows a few different things. So firstly, people are terrible at choosing their how to probe the robot's knowledge. So it seems like the growers that we worked with had no sort of conception about how the robot was learning, so they didn't really know how to test whether the generalization had occurred. Replay feedback, as you might have expected, didn't really show much about generalization, because it's just playing back the last data point, so that that had almost no effect compared to giving no feedback. Batch feedback, well, so this is the most time-intensive way of giving feedback, because for every demonstration you give 5 replays of the behavior, but that does actually seem to improve teaching behavior from our participants. Where do teachers go wrong? Well, these are just a few samples of where teachers gave poor demonstrations. So we saw kind of categorized 3 sort of error types. So the first would be demonstration error. So here on this side, a demonstration error is where a person was asked to give a demonstration, or was trying to give a demonstration from one particular location on the plant tray, but they actually gave a demonstration to a different location on the plant tray. So when they indicated which demonstration they wanted to do, somehow in the middle they forgot about what actually they were trying to demonstrate. That was a relatively uncommon error. So the total demonstration errors that we saw, the total counts of those kinds of errors that we saw across the cases, was order of sort of 3 or 4 per case. Another type of demonstration problem is undemonstrated state. So that's where only a few points were demonstrated and the remainder of the points were not demonstrated. So this is a bit of a double-edged sword. So if you only show demonstrations in particular regions, then of course this whole space here gets no demonstrations, and then generalization learning is poor there. But of course, if you're doing a good job of choosing your demonstration points, so those 5 points, for example, you would have quite a few undemonstrated states, but still see good generalization performance. And then we quite often saw cases of ambiguous demonstrations, that is to say, people giving repeated demonstrations to the same points on the plant tray. So from a machine learning perspective, from the robot learning perspective, we didn't, that doesn't give you any new information to repeatedly show that point. So it's a very inefficient way of teaching. But maybe there's something psychological about how you give demonstrations to other humans that means that you might be trying to, take that same approach. So often if we teach a person, we might teach them the same skill over and over so that they might reinforce their ability on that skill, and we kind of assume that the generalization happens anyway. But this isn't how it works with a robot. So it's kind of interesting to see where these kinds of errors go wrong. So I've only given you kind of a high-level overview of the results from this paper. Please take a look at the details if you're interested. So going a little bit further, going a little bit beyond that study, one of the things that we're interested in particularly at the moment is optimizing teacher feedback. So in that previous experiment, the batch feedback was expert selected. So we chose those 5 points because we, as people that design machine learning algorithms, we kind of knew that they're a good way of indicating generalization. Okay, but that's not really a scalable approach. So, the first thing is it's still quite subjective. How does the expert know that this is a truly optimal demonstration set? And it's not really transferable, so we don't really know how to extend that to different tasks, different learning algorithms, different robotic plants. There's lots of different factors that are involved here, and we designed chose a simple experimental task, but that's not going to work in all cases. So one of the questions that we're kind of grappling with at the moment is how can we ensure better teacher training sort of across tasks, so without that kind of expert selection need. So this is an area that we've kind of settled on and we've been quite interested in, is this approach of machine teaching. So machine teaching is kind of the converse of machine learning. Essentially the idea is that we have the learning problem, so the learner has to optimize their parameters of their model using some learning algorithm A applied to a data set D. The machine teaching problem is how can we generate the optimal data set D that will minimize some teaching risk, which somehow captures the difference between the parameters that are learnt by the learner and some desired set of parameters that the teacher somehow has in their brain. Okay, and the particular formulation that we've been working with also has an effort term within it. So we're talking about giving demonstrations subject to some sort of maximum budget on the teaching data that we are going to give. Okay, that's quite reasonable, I think. So you're not going to, it costs a lot of time to give a lot of demonstrations, and most people will get bored of it. So it's reasonable to assume that you'll have a maximum number of data points demonstrated, but it also, plays into things like, where on the robot and so on. So the hypothesis that we've been sort of following here is that novice teachers who are trained to provide optimal demonstrations on one problem will show enhanced teaching skill on others. Okay, so the idea is that we solve the machine teaching problem and produce optimal data for one problem. We teach our teachers, we train our teachers to give that kind of demonstration for that problem, and we're hoping that they're going to generalize their teaching skill so that they become better teachers for other types of problems. So this is relatively early work, but I wanted to share it with you. So we've been testing this just for a very simple problem of teaching dynamic behaviors on like a motor controlled pendulum. And of course, because of COVID, we've been doing this in a virtual environment and getting people to do teaching sort of online over Zoom calls or Microsoft Teams calls. So this is, the experiment that we're doing is teaching these different skills. We're assuming that we have a simple linear in the parameters learner, and we're assuming that the teacher is minimizing some difference between the desired motor skill parameters. As we have designed the motor skills, we know exactly what those parameters are, and the parameters that come out from a learner, and again, a simple ridge regression type learner we're using in this experiment. Okay. So all simple learning stuff. Okay, and from within this setup, you can show that the optimal demonstration set will basically maximize the determinant of the features. So the sort of the feature transformed data points. Okay, details of this can be found in this archive preprint, which is under review for the Roman conference. So let me jump straight to the results of this and sort of tell you, show you some of the things that are coming out from here. So the task was to teach dynamic motor skills by demonstrating keyframes, and we worked with 32 participants with no prior experience in robot teaching. And the way that we ran this experiment is that we got people to teach, firstly, we teach a skill with no guidance, and for a simple pendulum, these are skills like tracking a particular swing motion, or doing a stopping motion, so like a critical damping movement. So we had teaching of the first skill, no guidance, teaching of the second skill, no guidance, and then in phase 3 we did teaching of the first skill, but we gave guidance. So we separated our participants into 2 groups. We gave guidance to our target group, and that was a score based on the determinant, and we had a control group who had no guidance, so effectively they repeated phase 1 of our procedure. And then we continued, so we looked at, we repeated phase 2. So phase 4 was just a repetition of phase 2, so it's teaching skill 2 with no guidance. And this is to test whether, after being given guidance on the first skill, whether there's a change in the behavior on the second skill. And then we repeated phase 1 and repeated phase 2 again. Okay, so in each time we're trying to compare whether this intervention of giving guidance in phase 3 has influenced behavior in the later phases. So the interesting thing is that, okay, here we're comparing phase 3, I think it is, against phase 1 against phase 5. So here we're seeing an increase in the quality of teaching, so the teaching score, which is related in to determinant of phi, is increasing for the target group, but staying roughly the same for the control group, as you might expect, because the control group didn't get any guidance to change it. And there's a significant change in that teaching quality. This is also reflected in the root mean squared error of the trajectories reproduced by the learner. So the learner error decreased for our target group, whereas it stayed the same or actually slightly increased for our control group. So it shows that we get increased teaching quality in our target group after being given guidance. And then we compared the case where you are we compared P2 against P4. Okay, so this is the interesting one because this shows the difference, whether giving that guidance on one skill improves teaching behavior on a different skill. Okay, and as you can see, our target group had an increase in the teaching quality metric, which is measured by the determinant, which was significantly greater than that of the control group. And again, a reduced error in the reproduction of that skill by the learner. Okay, so although this is still relatively preliminary work, it's kind of interesting. So we get increased teaching quality after guidance, even for a skill where no guidance was given. Okay, so this encourages us that by training people to be better teachers on one skill, they actually become better teachers of robots in different skills too. So that's quite exciting. Okay, and now the final part of my talk, I want to sort of switch gear a little bit. So this is work that we've been doing in collaboration with that herb and salads producer. Now there are some tasks for which it seems like, well, possibly infeasible that you could really effectively learn these tasks, at least at the current state of the art of robot learning. So this is a task that is particularly important to our industrial collaborators, that is the manual handling of fresh herbs. So they buy in these, they either grow or they buy in these bales of fresh herbs. This is basil here. And the task that they have is trying to pick out a specific amount of this herb to be packaged and sent off to a retailer. Okay, so you might try to get 15 grams of basil out of this big box or crate of basil. So this is one of the highest labor costs that you get in this area. So roughly 50% of the operating cost goes on this low quality, sort of low skilled labor. And it's also one of those jobs which is really hard to recruit people for because it's dull, it's repetitive, and it's actually cold work. So you'll be working in a refrigerated pack house. So this is really, not pleasant work to be doing. So the challenge that they are facing is how can you enable automation for this, and in particular automation for lots of different herb types. So not only basil, but coriander, parsley, rosemary, and so on and so forth. So, thinking about how you might, try to imitate the way that people are doing this kind of behavior, it just seems, fairly impractical that we will really learn at least in the near term, this kind of behavior. So here we're doing some tracking of, so this is basically teleoperation of the robot trying to pick out sprigs of rosemary based on motion sensors in this glove. And we just, our company couldn't sort of feasibly see that this is a practical solution, for them. So, this is taking a lot of time and it's just not really working very effectively. So we've been looking at how we can do, how we can break into this problem for simpler types of grippers like parallel grippers. And one of the things that we noticed when working with this type of herbs is one of the major problems, one of the major uncertainties that you have to handle is the factor of tangling in herbs. So here this gripper is trying, has just done a little pinch grip to try to pick up this, I think this is parsley. And the gripper ends about here, but because of the tangling, we've got all this extra bunch of parsley here. So the question is, how can we mitigate this? How can we, get more consistent picking? So the approach that we've been exploring here is what we're calling the spread and pick approach. So the idea here is that we want to seek good places for doing picking and try to improve the consistency by reducing tangling at the point of the pick. And it's a very simple sort of idea is when you go in to do your picking behavior, you find a tangled point and then you spread that point out by widening your gripper plates and then grip again and lift up. So it turns out that even that very simple idea takes quite a bit of complex processing. So the approach that we've been taking here is to make use of what's called the graspability index. So this is an index that has been proposed in the past for gripping objects from a bin, where you're trying to basically find a point where you can do a grasp, without colliding with other objects and enabling you to pick out a single object from a possibly tangled pile. Okay, so it essentially works on using depth map images, and you have two pipelines. One of them is seeking the highest point within your collection of objects and seeking out where is the right place to grip that object, and seeking out the points where, for a given insertion depth, you might have a collision with one of the other objects. So here we've got a target object here and the two other objects here and here. And so we're seeking out places where if we put our gripper, we're going to end up with a collision with these other objects which are not our target object. Okay, and it turns out that by thresholding and convolving these depth images together, you can come up with quite an effective graspability map, which shows you a point which, if you pick there, you should have a good chance of picking the object without colliding with any other objects. Now, the key to our approach is basically abusing this a little bit by seeking points where we have using the second pathway as a way of detecting where we have highly tangled regions. Okay, so the idea is that within regions where we have a lot of material, we're more likely to, for a given insertion depth, we're more likely to detect the chances of collisions. But because of what we're handling, the collision is not so important. So the idea is that within those regions we'd be able to get the most impact of doing that spreading behavior. Okay. So again, for full details, have a look at the IROS paper on it. But essentially, what we're doing is we're taking an image such as this one, and we're finding the collision-free point. So that's the traditional graspability index point, and then we're finding the point at which we have the highest chance of collision at a certain insertion depth, and then we basically form a line between those 2 points, which is our spread direction. Okay, and then from that spread direction, we know that that's the point where we're going to get the most impact by spreading out the herbs, so that we can improve the consistency of the picking. So by taking this approach, we've tested this on a combination of both plastic herbs and fresh rocket. This is rocket salad. Interestingly, from it, we managed to see something like a 29% reduction in the picked weight variance for separate piles of herbs, and a 56% reduction in the picked weight for herbs which were previously unseen. So it was surprisingly effective. Just this simple spread allows us to get significantly higher consistency in the amount of fresh herb that we're picking when we do this. Okay, so in summary, I think that within this area of fresh produce manipulation. There's a lot of low-hanging fruit in terms of automation. There's a lot of things that can be automated here. But in my view, putting power in the hands of growers is the key to actually really getting this sort of technology rolled out in the real world. Programming by demonstration needs both advances in the algorithmic side of things, which is what we've been doing a lot of work on, of course, but it also needs some consideration of their usability. And I think that we've only just started sort of scratching the surface of what kinds of things we need to do to make it practical for novice users to work with. So with that, I'd like to thank you, and I'm open to any questions in the session later.